262 degrees. So if we go to our plot where I was plotting it out, I plotted it as, 1.42 at 259. Okay, so that's our original data. I was just using one transducer for doing the balancing and checking to make sure that they're both kind of changing with each other. Keeps the math down.
If you're using one.
It's quicker and easier to use one if you don't have a computer doing the calculations for you.
Okay.
But yeah, 1.42 at 259. And then we went ahead and installed the 350 grams at 0 degrees, lined up with the laser tape. And we go back to our data here. I believe will be run 2. Yep, so during this run, we had 0.908 at 207 on that same transducer. So 0.908 at 207. We go back to our plot. So very similar numbers. It varies a little bit with time, so it depends on where I took the actual sample. But we plot this out, 0.925 at 204. You look at the phase markings on the plot, so 0.925 at 204. Now what we want to do is see how this vector is changing, and we do that by drawing a vector from the tip of our original vector to the tip of our trial vector, and that's this red arrow here. And that is the change in vibration due to the installation of the weight. And if I replot that line over here, I get that it changed by about 1.3 inches per second at 122 degrees. So right along this line right here. Now, you can, at this point in the balancing process, you can choose to leave the weight on and add more weight, or cut the weight off and rotate the weights to a new location. In this instance, we opted to cut the weight off and use the same weight again, because if we're balancing out our original vector, it's at 1.4 mils, and our change vector was inches per second, 1.4 inches per second. Our change vector was 1.3 inches per second. That, if it works out exactly, that would get us to 0.1 inch per second vibration if it worked perfectly, which it didn't. But nonetheless, it was looking like the amount of weight we put on there was pretty close to exactly what we'd want to put on it to balance it out. So we cut it and we rotated it to a new location. And how we chose the location to rotate it to was, when we remove the weight, we're going to go back to our original. So therefore, we want the weight to act 180 degrees out of the original. So if I just draw a line going 180 degrees out, and I count from the tip of this vector to this line right here, it's about 5, 10, 15, 20, 25, 30, 35, 40 degrees. A little over 40 degrees, maybe like 42 degrees. So all we want to do is rotate the weight 42 degrees in the direction of rotation. So that would be taking this weight, and instead of installing it at 0, we'd move it 5, 10, 15, 20, 25, 30, 35, 40. So it'd go right there. Yep.
So the weight goes in the opposite direction of the rotation of the shaft.
Well,
Oh, the same.
Follows.
Yep.
It's 180 from the imbalance.
Yep, gotcha.
we want to move our change vector so it acts 180 degrees out from the original.
Yep.
And yeah, in this case, it was rotating at 40 degrees this way. If this vector was over here, let's say it was over here and of this magnitude,
Go the opposite
we'd want to
direction.
rotate it, 30-ish degrees this way.
Right.
And we'd also want to reduce the amount of weight.
Right.
And if it was, this magnitude, we'd want to increase the weight. And after installing the, trim balance, trim weight, we had about 0.75 inches per second at around about 252. So it didn't work out perfectly, but it did, improve things over the other two cases.
And that was while the weld was still hot?
The welds had, for the most part, cooled down on that one.
Okay.
We actually did have better results last night balancing with washers. But do we think this one's cooled down enough yet? A little longer?
She's pretty close.
She's pretty close. Okay. All right. Give it a little longer. Yeah.
Do you need to take off soon?
No, I'm good for the moment. I got another hour and a half I can hang out for before I need to load up and boogie. Oh. Is there any